In this lesson, we're going to continue where we left off in our previous lesson and continue to develop exponential equations to model situations of exponential growth and decay. And we remember growth is going to happen when our base is greater than 1 and the graph is going to increase, and decay is going to happen when our base is less than 1 but greater than 0 and the function is going to decrease. Let's start off with the first question. It says an antique vase was purchased in the year 2000 for $8,000. If the vase appreciates in value by 6% per year, what's the estimated value in the year 2040? So this is an exponential growth question because it's going to increase in value. So our base should be greater than 1 so that every year the vase gets more and more valuable. So let's start off by understanding the problem with the t-table if you need it. So our independent variable is going to be time, but I don't want to put the year 2000, 2001, 2002 here because I'm trying to find a connection between my x variable and my exponent. So instead, I'm going to put the years 0, 1, 2, and 3, and I'm going to call this variable time since, or years since the year 2000. So that means that this would be, if it's been 0 years since the year 2000, that is the year 2000. This would be 2001, 1 year since. The next one would be 2002, 2003, etc. So now I can make my y, or my dependent variable, the value of the vase, so value. So let's fill this out now. So let's start to fill out what we know about the value. So we know in year 0, which is the year 2000, the vase is worth $8,000. After a year, it appreciates in value by 6%. So that means we're going to take that 8,000. We're not going to multiply it by 6% because that's just going to give us the change in value. We want to include the value of the 8,000, so we're going to multiply it by 1.06. And if you multiply those two together, you get 8,480, which is a reasonable number. It's not increasing too much, but it's increasing, so we know that we're on the right track. So for the second year then, it's going to appreciate in value right from this value here. So it's again going to increase by 6%. So we know our next value is going to be 8,000 times 1.06, which is our previous value. And then we're going to multiply it by 1.06 again, so that becomes squared. And our last one again becomes the previous value, 1.06 to the power of 2, but then multiplying 1.06 again, we get to the power of 3. Now that we've got this, we can see our pattern and we can start to come up with our formula. So we know that our value is going to equal, we're going to start off with 8,000, that's our starting value. And then take a look at the connection between our number of years since 2000, so our x variable, and our exponent. So we have a little exponent 1 here, and that's an exponent 0. We could rewrite this as 1.06 to the power of 0. And so, take a look here, we can see that our exponent is just whatever our x value is, as long as we've defined it correctly. So, continuing with our formula, we've got 1.06 to the power of n, and we've got to find those v's and n's. So our n is going to be defined as, the number of years since the year 2000. And our v is going to represent our total value of our vase. So now that we have our formula, we can use it to answer the question that was asked of us, which is what's the estimated value in the year 2040? Well, if the year is 2040, then we know that our n value is going to be 40. And that's because it will be 40 years since the year 2000. So now that we have our n value, we can sub it into our equation. So we'll have v is equal to 8,000 times 1.06 to the power of 40. Throw that into our calculator, and we get 82,285 and 74 cents. So the moral of the story is we should all go buy an $8,000 vase right now. Because in 40 years, it's going to be worth $82,285.74. Okay, our next question is similar, except it's a depreciation question because our thing is going to decrease in value. So it says a 2017 Honda Civic just depreciates by 15% per year. The car was purchased for $18,000. Find the value of the car in 3 years. So we could just figure this out with the table of values. Let's just practice because the number of years isn't too long. But let's just practice making an equation and then we'll plug in our years to find the solution. So just as a side note to get started, if the car depreciates by 15% per year, how much of its value does it keep? And that answer is it's going to keep 85%. And I got that because I just took 100% and we took away 15% because that's what's decreasing by. So we're going to be left with 85%. So if we start off with a table of values here, on our independent variable is going to be time in years. And our dependent variable is going to be, again, value. So let's throw in years 0, 1, 2, 3. And again, at 3, we're going to get our answer. But we're just going to practice with the formula. We know our value starts at 18,000. So that's what we know our value is in year 0, which is the year 2000. And just looking at what I defined as my X value, I said time in years, but I should be more specific. It's time in years since the year 2017. So let's add that here. So I've changed my X value to years since 2017. So year 0 would imply the year 2017. We know it's worth $18,000. So now it's going to depreciate in value. So how much is it going to be worth the next year after 1 year in 2018? Well, it's going to be worth 85% of 18,000. So we know that its value is going to be 18,000 times 0.85. So it's going to decrease in value. This is going to be a decaying function because we're multiplying our initial value by a number that's less than 1. So it's going to decrease in value. And we know that's really an exponent 1 here. The next year, we're going to take the exact same value, 18,000 times 0.85, and we're going to multiply it by 0.85 one more time, so that becomes squared, so it's 85% of that. And finally, we have 18,000, 0.85 to the power of 3. So now we're ready to write our equation. So we know that the value is going to equal, just taking a look at this pattern, we're starting with 18,000, we're multiplying by 0.85, it's going to be to the power of whatever the number of years are since 2017. So we're going to have the value is equal to 18,000 times 0.85 to the power of n, or whatever it is that you define, and let's define our variables. So we know that n is going to be the number of years since the year 2017. And we know that v is just going to be the total value of the car. So if we need to find after 3 years, then obviously we're just going to plug in n is equal to 3. And we're going to be given the equation v equals 18,000 times 0.85 to the power of 3. And we'll get $11,054.25. In our next example, it says that a certain type of bacteria doubles every 20 minutes. So this is a doubling time question. If the original size of the bacteria culture is 30, that means that we've got 30 bacteria to start. How many bacteria are there in 3 hours? So again, we can figure this out with the table of values because the number of hours is quite small. But let's practice with creating an equation. So again, we're going to start off with our table of values. In this case, our independent variable is going to be the time. And it says it doubles every 20 minutes. So let's do the time in minutes. And our y value is going to be our population of bacteria or the number of bacteria. So now let's start to fill in our t-table. So think carefully about what would be nice numbers to put in here because it says it doubles every 20 minutes. So it's not going to be helpful to me to go up by 0, 1, 2, 3, 4. It would be more helpful to go up by 20-minute periods. So that's going to be my starting point at 0 minutes. And then what's going to happen after 20 minutes, 40 minutes, 60 minutes, etc. We can even go one more if you're not sure. So we can do 80 minutes. So now let's figure out what would actually happen to our population of bacteria. So we know that it's starting at 30. That's the original population or the size of the culture. After 20 minutes, it should double, which means it's going to be 30 times 2. After another 20 minutes, it's going to double again. So we have our amount, 30 times 2, and we're going to multiply it by 2 again. And after 60 minutes, the same thing's going to happen. We're going to have 30 times 2 to the power of 2, multiplied by 2 one more time, and we have 3, and the pattern continues. Next, we're going to have 2 to the power of 4. So now we've got to come up with our equation. But this is the first case we've seen where our exponent is not exactly our x variable. So we've got to try to find a way to calculate this variable. Well, we know that this is 2 to the power of 0 if we wanted to add that guy in there. So we know that how could I get 1 from 20? How could I get 2 from 40, 3 from 60, and 4 from 80? Well, if I take these exponents, 1 is equal to, if I take my x value, which is 20, and divide it by 20, which is the doubling time, I'm going to get 1. For 2, let's see if this pattern continues. If I take my x value, which is 40, and divide it by how long it takes to double, which is 20, I get 2. One more time. If I take my x value, that's 60, divide it by my doubling time, that's 20, I get 3, and so on and so on. So if I take 80 and divide it by 20, I get 4. So this exponent is actually just the number of doubling or number of times that the bacteria has doubled. And to figure out that, all I have to do is take my time and divide it by how long it takes to double. So 20 divided by 20 is 1. 40 minutes divided by 22, 60 divided by 23, and etc., etc. So if I was going to create an equation now, I would say the number of bacteria, let's say that's capital N, is equal to, we know we're starting off with 30, and we know that our base, or our growth factor, is going to be 2, or our base is 2. And then our variable, we're going to take the number of minutes, so maybe we say that's m, divide it by the doubling time, which is 20, and that's going to give us our exponent. So that's the pattern that we found, the minutes divided by 20. So now let's define our variables. We know that m is going to be the number of minutes that the bacteria is left to grow, and n is going to be our total number of bacteria. So now we have our final equation. So the difference with this one is that, again, our exponent didn't exactly match whatever our x value is. So we had to figure out how to come up with our exponent from our x value. So we figured out that we're just going to divide it by the time it takes to double. And now we can solve the question. So the question gives us how many bacteria are there going to be after 3 hours. So 3 hours, we need to figure what that is in minutes. So it's going to be 3 times 60. It's going to be 180 minutes. And now we can plug that in to our equation. So in our equation, we've got n is equal to 30 times 2. Our minutes are 180. We're going to divide that by 20. And we'll get n is equal to 30 times 2. 180 divided by 20 is going to be 9. So that means in that period of time, it's going to double 9 times. And our final answer is 15,360 bacteria. Now the next question is a little bit different. It says if left uncontrolled, meaning it's going to continue to grow and grow and grow and nothing's going to stop it, approximately how long would it take to get to 3 million bacteria? So taking a look at our equation, we were given the number of minutes or the time previously. Now we're given the number of bacteria and we have to solve for our m. So let's start by copying down our equation that we created. Now we're given the total number of bacteria, so let's add that in. We know our number of bacteria is 3 million, so 3 million is going to equal 30 times 2, all to the power of m over 20. We've got to solve for this exponent, and the only way we know how to solve in grade 11 is by guessing and checking. So we have to get this exponent as by itself as possible, so one thing we can do is we can get rid of that 30. So we're going to divide by 30 on both sides. And we're going to be left with 100,000 on this side is equal to 2 power of m over 20. So now in grade 11, the only thing we can do is guess and check. So we've got to make this a like base to this guy over here. So on the right, we have a base of 2. So on the left, we also have to create a base of 2. So we have to find an exponent that when I plug that in, it's approximately equal to 100,000. And once I know what that exponent is, I can set these two equal to each other. So once you play around with it for a little bit and check some numbers, approximately, if you put in an exponent of 16.5, to the power of 16.5 is 92,681, which is approximately equal to 100,000. So I'm going to add in my little dot here because now we're dealing with approximates. Okay, so I can draw a conclusion then. Therefore, if those are approximately equal, then 16.5 is approximately equal to m over 20. And now we can just solve for m. So I'm going to multiply by 20 on both sides, cross this guy out, and I'm left with 330 is equal to m, which means that it will take approximately 330 minutes for the population to reach 3 million. So in our next question, we're going to work with money. So it says a $13,200 bond earns 4% interest per year. So what a bond is, it's like a loan to a company. So if a company needs money, they might issue bonds. So you're lending a company money, but they're going to give you interest in return. So they're going to give you your full amount after a certain number of years plus interest. So this says, what is the value of the bond in 25 years? And a piece of information that's missing is that this is compounded annually. So let's add that piece of information there to make sense. So now let's go to our table of values. So on our x-axis, we're going to have time in years because that's how time is measured in this question. And on our y-axis, we're going to have total value. Okay, so choosing our x values, there's nothing funny that's going on in this question. It's just going to increase by 4% per year. So I'm just going to go up by ones here, 1, 2, 3. And our value, we know it starts at 13,000, so let's add that in here. Sorry, $13,200. And then the next year is going to be worth 4% more than that. So that means we're going to have our initial amount, 13,200. Then we're going to multiply it by 1.04. So it keeps the value of the 13,200 and adds 4%. The next year, if interest is compounded, that means we're going to take the amount from last year and find the interest on that. So we're going to multiply by 1.04 again. And one more time, 13,200, we're going to multiply the previous value by 1.4 one more time, and we get to the power of 3. So putting it in, creating an equation now, we have our total value is going to equal our initial amount, 13,200, multiplied by 1.04. Looking at our pattern of our exponents, I have an exponent 1 here. So our exponents exactly match the time in years that we've held the bond. So I can go ahead and write n maybe for a number of years and define our variables. So our two variables are going to be n, which are the number of years our bond is held, and v, which is the value of our bond. So the next question, we know what's the value of the bond in 25 years. So we know that our n is 25. We're going to sub it into our equation and see what it equals. So we have 13,200 times 1.04 to the power of 25. And our value is going to equal 35,189 and 4 cents. The next question asks, given everything we figured out in part A, approximately how long would it take to double in value? So let's start off with our equation that we found. Our value is going to equal our original amount, which is 13,200, multiply it by 1.04 every single year to the power of the number of years that we've held it. So if it says how long would it take to double in value, it means how long means we're looking for n and we're given our v. So if our original amount, or if our original value was 13,200, double that would just be multiplying it by 2. So our new value is going to be $26,400. So what it's asking is how long would it take to get to a value of 26,400? So let's plug that into our equation and check. So we're going to plug in our value is going to be 26,400, which is equal to 13,200, 1.04 to the power of n. So we want to get n as by itself as possible. So let's divide by this 13,200 on both sides. And we're going to be left with, on the left side, we're going to be left with 2 because we know it goes into it 2 times. we're going to have 1.04 to the power of n. So now, again, in grade 11, all we can do is do a little bit of guess and check. So we need to make these bases match. So my base on the right is 1.04 to the power of n. I got to make 2 into 1.04 to the power of some sort of exponent. So try in your calculator and approximate. What should that exponent approximately be? So if you play around in your calculator for a bit, you might come to a value of approximately 18. So if I were to put 18 in there, 1.04 to the power of 18 is approximately 2.0258, which is pretty darn close to 2. So we're going to say approximately this is equal, and so therefore we can draw the conclusion that 18 is approximately equal to our n. So the number of years it will take to double in value is 18 years. So we're on to our last question now. It says an element has a half-life of 100 years. So half-life is the opposite of doubling. It means that some population cuts in half after a certain number of years. So we were talking previously about a doubling time question where a population doubled every so often or every certain number of years. Now, this is a decaying question where something's going to cut in half every 100 years. So it says that this element, there was originally 80 grams of it. How much is left after 650 years? Well, just think about how many times is it going to cut in half in that time. And you can figure it out in your head very quickly. It's going to be 6.5. So let's work that out in a table of values. So once you set up your table of values, your x value should be the number of years. And your y value could be the total amount in grams. So if we were to pick out some values for x, it doesn't make sense to go up by 1, 2, 3, 4, etc. Because after 1 year, it's not going to cut in half. And after 2 years, it's not going to cut in half. After 100 years, it's going to cut in half. So let's start off with 0, and let's count up by 100. So what's going to happen after 100, 200, 300, etc.? So let's start filling in our value now. So our value after 0 years, so no time has elapsed, we know it starts at 80 grams. And then after 100 years, we know that that 80 is going to cut in half. So we're going to multiply it by 0.5, which is the same as dividing by 2. After the next 100 years, that value is going to cut in half again. So we're going to take that 80 times 0.5 and we're going to multiply it by 0.5 again. So it becomes 0.5 squared. And the year after that, we have 80 times 0.5 squared, all multiplied by a half again. It's going to be to the power of 3. So filling in this exponent, we know that's an exponent of 1. And we've got to draw a connection of what our exponent is and connect it to our x value. So we can see that this is so similar to the doubling time question that we saw, where we can find our exponent by just taking our number of years and dividing it by how long it takes something to cut in half. So the half-life, and that's 100. So one more time, we can break this guy up. This exponent is equal to, take the number of years, which is 100, and divide it by the doubling time, how long it takes to double. 100. 100 divided by 100 is 100. Let's try 2. Take the number of minutes, years, which is 200, divide it by the doubling time, you get 2. Then this guy, take the number of years, 300, divided by the doubling time, and we get 3. So let's make this into our own equation. So we have the total amount. So let's say that that's A. Our total amount is going to equal, starts with 80 grams. We're going to multiply it by 0.5, but our exponent is going to be take the total number of years, let's say that's n, and divide it by the half-life, how long it takes to cut in half, which is 100. So let's quickly define our variables. So our n is the number of years and our a is our amount in grams. So it asks us how much is going to be left after 650 years. So that means that our n is going to be 650. We've got to throw it into our equation. So if a is equal to 80 times 0.5, we've got 650 all over, there shouldn't be a decimal there. So 650 all divided by 100. So that's going to be a is equal to 80 times 0.5 all to the power of 6.5, which is the answer we came to at the beginning of the question. So if we throw that into our calculator, we get 0.88 grams. So if it cuts in half over and over and over again. exactly 6.5 times, we're going to get 0.88 grams. So after 650 years, there will be 0.88 grams of the element left. So we've reached the final part of the last question. It says, approximately how long would it take for a different sample to decay to 1/5 of its mass? A different sample means that we're not starting with 80 grams anymore. We don't know how many grams we're going to start with. All we know is it's the same element, so it's going to have the same half-life. The half-life is still going to be 100 years. So every 100 years, the entire mass, which we don't know, is going to cut in half. So because we don't know what the original amount is, let's make a letter to represent it. So how about we use, I don't know, M. Let's say M. So let M represent the original amount. The original amount in grams. So let's revisit our equation then. We have our total amount, which is A, is equal to, instead of 80, we don't know what that is. So we're going to put M. So it's our original amount, and then we're going to times it by 0.5. It's going to be all to the power of number of years divided by 100. So it says approximately how long will it take for this sample to decay to 1/5 of its original mass. So that means the amount that's left over here has to be 1/5 of its original. Well, 1/5 of its original is going to be 1/5 of M. So that's what our final amount is. Our final amount is 1/5 of M, and that's got to equal M times 0.5 to the power of N over 100. So one more time, we have no idea what the original amount is. No problem, we put in a letter there to hold its place. We know that the final amount has to be 1/5 of its original, so it's going to be 1/5 of M, or another way to say that is M over 5. So now we have to solve for our exponent. So we have one equation and two unknowns. So normally we wouldn't be able to solve this. However, if I get rid of M here, to do that, I'm going to divide by M. So I'm going to divide by M on this side. I've got to divide by M on this side, and something beautiful happens, and that our M's cancel out. So M divided by M, that's just going to be 1. M divided by M on the other side is also going to be 1. So we're left with, on one side, we have 1/5 is equal to 0.5 to the power of N over 100. And so now we have one equation, one unknown. We can solve this. So first let's change 1/5 to just 0.2 to make our life a little bit easier. Is equal to 0.5 N to the power of 100. And now the only way we can do this is by creating like bases, and we're going to do some guess and check. So if 0.5 to the power of something is going to be approximately equal to 0.2. So we have 0.5 to the power of N over 100. So 0.5 to the power of something is equal to 0.5 to the power of N over 100. So we have to figure out what exponent here can I throw in there that will approximately equal 0.2. So try it on your own. So once you play around your calculator a bit, if you throw in an exponent of 2.5, it's not exact, but it's approximately 0.2 because it comes out to 0.17677, which is approximately 0.18, which is pretty darn close to 0.2. So let's draw the conclusion that approximately, therefore, 2.5 is approximately equal to N over 100. And we know we can solve for that N now by multiplying by 100 on both sides. And we're going to be left with 250 is equal to N. So that means it will take approximately 250 years in order for the mass to cut down to 1/5 of its original size.